All right. So this is the second question. Even from observing this circuit, we can find out that there is no resistor in series with this inductor, unlike the previous question, and there is no capacitor in parallel with any resistor. That makes our life a little bit harder. Now, also, but it's not a problem. We can resolve it, but also, or we can solve it. But also, if we look carefully, we can see that this is allowed because it's IB. That is the current of a current source. This is a current source, and it's the current of a current source, so it's allowed. It's going to be in our final equations, or it might likely be. It qualifies for being in our final equation. We also see IL. Yeah, IL can also be. Then inductance, capacitance, and resistance can also be. So let's proceed. So now, the first step is to look, to scout for, to try to observe, to check out, to inspect the circuit for memory elements. In case you don't know what memory elements are, it's not a problem. Any reactive element is a memory element. So there are two reactive elements, inductor and capacitor, and that's it. So whether they call it energy saving element or memory element, they are talking about inductors and capacitance. So we have two memory elements here. Therefore, we are going to have two differential equations. So you pick any one you want to start with. It's okay. And by the way, I don't usually, I'm not even concerned with voltages at each node because for me personally, the voltage across an element is sufficient. So this is ground, right? This is ground already. I know that is zero. This is reference. The voltage across the inductor is the same voltage on the node here, on this particular node, on this at this point here. So there's no need to account for that. Then if you want to call here a node, the voltage across the resistor is also the voltage at the node here too. So what's the point? You know, that's the reason why I just want to, my goal is to strip as many details as possible, reduce the details as much as possible. It makes my life easy or easier. So having said that, we just begin with one of the memory elements, and if you like, you can begin with the capacitor, you get the same result. If you like, you begin with the inductor. So I'll start with the inductor. Now, the voltage across an inductor is equal to the inductance of that inductor multiplied by the time derivative of the current through the inductor, the time derivative. Haven't arrived at this equation. The next thing you look at is the left-hand side of this equation. Yeah. So because you have voltage there, and it's the voltage across the inductor, you look for, because it's voltage, then you apply KVL. It makes your life easy because it's voltage. And so you look for the nearest loop or mesh and pick your choice that you want to use to solve it. Let's try the first mesh and see what happens. So I'll pick mesh 1. I don't think I'm going to get a good result, but let's see. Let's continue. So I've picked mesh 1. If we go around, because this is the direction of current, if we go around the direction of current, voltage across the current source would increase because it's supplying energy to the system. And then if we go down the inductor and in the direction of current, the voltage across the inductor will reduce. So therefore, UIB minus UL is equal to 0. But this doesn't give us much information, honestly speaking. It doesn't really help too much because, I mean, how do you now determine the voltage across the current source? And by the way, the fact that it's a current source does not mean that it does not have a voltage across it. Every current source has voltage across it, and every voltage source, if it is a closed circuit, has current flowing through it, right? Yeah. So it's called a current source because it maintains constant current. And it's called a voltage source because it maintains constant voltage. But they both supply power. And in power, for electrical power, there is a component of voltage and a component of current. So current sources also have voltage across them, but the voltage across a current source it varies, it's not constant because current is constant. So voltage depends on the load. That's why it's a current source. But in voltage sources, the voltage is constant, but the current depends on the load, right? So let's move on. So we cannot use mesh 1 alone. It's not sufficient because it's very few variables. So let us try mesh 2. Going in the direction of current, let's start from here, minus UC. And why is it a minus? Because in the direction of current, there is a drop in voltage across energy consuming or energy saving element. If it's supplying energy, right, it will be an increase. Otherwise, it's a drop. So minus UC minus UR, that's voltage across resistor. And then, so we've gone around all of this in the direction of current. Now, coming up towards the inductor, we can see that we are going against current. We're actually literally going against current. See, current is coming down and we are going up. So therefore, that will be a plus. Plus, the voltage across the inductor is equal to 0. And this might be more meaningful than the first one. So, in this equation, the voltage across the capacitor is allowed, so that will remain. The voltage across the resistor is not allowed, so we have to substitute or eliminate. The voltage across the inductor, it's what we need. So let me call this equation 1. This differential equation, let me call it equation 1. So you can see we will need to substitute this one here. So we also leave this one. I always like to leave it last just in case the structural equations become more complex to solve. So what we're going to deal with is U arrow. So let me take U arrow out. The voltage across the resistor using Ohm's law is resistance multiplied by the current, and the current is IC. Good. So we'll call this equation 2. So now you can see resistance is allowed, but current of the capacitor is not allowed. So now that we've gotten here, what do we do with IC? I could have said that we should, because we have current here, we should make use of KVL, but we've already made use of KVL. We're coming from KVL. So the only thing that is left here is the node analysis here, right? So because if we make use of KVL, we're going back to where we started from. So if we go back to the circuit, we can see that we can make use of Kirchhoff's current law. We can make use of it at this node or at this node. So I'll go with the first node. Let's call it node A. So at node A, the current from the current source. So I like current coming into a node to be positive and current leaving to be negative because it's intuitive for me to see that way. Anything coming into somewhere is a positive, while something leaving is a negative, sort of. So the current of the current source minus the current of the inductor minus the current of the capacitor is equal to 0. And you know the beautiful thing here? Inductor current is allowed. Current source current is allowed. So we can say that inductor of the capacitor is equal to inductor of the current source subtracted from the the inductor current, yes. So we can call this one equation 3, and we can call this equation 4. So we can substitute equation 4 into equation 3, and then we have the voltage across the resistor is equal to the resistor multiplied by the current of the current source multiplied by the current of the inductor. Yeah, we can call this equation 5. We can substitute equation 5 into equation 2. And so minus UC minus bracket arrow I subscript B minus I subscript L plus the voltage across the inductor is equal to 0. If we expand, we have minus the voltage across the capacitor minus the product of resistance and the current of the current source plus UL is equal to 0. All right. So let us inspect this equation and see if there are still variables that are not allowed. UC is allowed, R is allowed, current of the current source is allowed, resistance is allowed, the current of the inductor is allowed, but this is not allowed. However, we always reserve either the voltage across the inductor or the current through the capacitor. We always reserve it last. I usually reserve it last in case the mathematics or the equation becomes more complex. So now we can make this one, the voltage across the inductor, we can make it the subject of formula. So UL is equal to U subscript C minus, plus arrow minus. Yeah, so when we look at this, we can see that everything inside here is allowed. So what we'll do next, the last step we take is to substitute the right-hand side of equation 1 in equation 6. So therefore, this will be our final product, our final answer. So we've solved for the first case. So the next thing we'll do is to also do this exact same steps, like similar situation, a similar set of steps for the capacitor. So we know that for a capacitor, the current through the capacitor is equal to the product of its capacitance and the time derivative of the voltage across the capacitor. Let's call this equation 8. So we have this equation, this differential equation. What do we do with it? We try to find structural equations that we can use to manipulate for the left hand side. So we have IC. Let us go back to the circuit. Where is the capacitor in question? This is the capacitor in question, right? Good. Because we have IC, we can make use of KCL, right? Kirchhoff's current law. And if you look at the capacitor, it has two terminals. You can go back or you can go forward. And then you see the nearest nodes to the capacitor. There is one here, there is one there. So they are the capacity, they are the nodes that we can make use of. Anyone you want to pick, you can, but I'll pick node at node A. So we have that at node A, IB minus IL minus IC is equal to 0. You see? So we can substitute IC for this one, but let's not do it now. Let's do it as the last step. The third question we're going to solve will make us see why. But for now, let's continue with this. So now we have IB, we have IL. IL is allowed to be in the final equation, but IB, and IB is allowed to be in the final equation too. Damn, we've solved our question. That means we can proceed quickly and end this. So making the current through the capacitor the subject of formula, we have that IC is equal to IB minus IL. Therefore, because we can substitute now, C du subscript C divided by the T is equal to IB minus IL. I'm a bit surprised. I was expecting more difficult. Or did I make a mistake? I didn't make a mistake. It's correct. Yeah, so that's it, basically speaking. So we'll go to the third question. The third question is more involved, and we'll see the reason why I like taking this step, like putting in the differential part of this differential term, putting in at the last step. We'll see the reason why. Because the next question involves, at a point you have to now start factorizing in some kind of ways that will make it inconvenient to be factorizing with this differential part. So let's go to the last question, the third and the last question.